Isaac Newton's insights set the course of science for hundreds of years. But there's a sense in which Newton's insights were also deeply misleading. Newton's famous laws of motion codify what we all experience in everyday life. Things move, and as they do, they sweep out trajectories defined by position, where something is, and velocity, how fast and in what direction something is moving. Indeed, reality in this framing comprises these very trajectories. By providing equations to delineate these trajectories, how the position and velocity of an object change over time, Newton provided an algorithm for predicting how reality unfolds. And the algorithm works. Newton's laws correctly predict where the moon should be at any moment, where the planet should be at any moment, where a ball should land when thrown. But in the early part of the 20th century, as scientists began to probe the newly accessible realm of molecules, atoms, and subatomic particles, Newtonian predictions failed to describe the data. And this failure was not one of fine detail that might suggest a simple refinement to Newton's equations. The failure was epic, suggesting to some that an entirely new paradigm might be required. That intuition proved correct. And remarkably, by the late 1920s, a single generation of scientists produced that new paradigm with the discovery and development of quantum mechanics. An essential feature of the quantum paradigm is that the theory is built around the concept of probability. That is, unlike the Newtonian picture in which we specify how things are now, and the equations predict how they will be later on, in the quantum picture, we specify how things are now, but the equations do something entirely different. They dictate the probability of how things will be later on. And according to our best understanding, the reliance on probability is not a limitation of the approach, but rather is a fundamental feature of reality. The universe, in a manner that Einstein found unpalatable, evolves according to a mathematically precise game of chance. So why don't we see these probabilities in the course of everyday life? Well, the large scales of the everyday, compared to atoms and particles, skew the probabilities, making one outcome the almost certain outcome, and that outcome is indeed the Newtonian outcome. But as we consider smaller realms, the probabilities spread more broadly, rendering the Newtonian outcome just one among many possibilities whose likelihoods are governed by the equations of quantum mechanics. Einstein may have been the most vocal critic of this direction physics had taken, but even ardent proponents have struggled to grasp what quantum mechanics really means for the nature of reality. Although experiment has confirmed quantum mechanics to astounding precision, and scientists have used it to develop stunning technologies, many of those questions are still with us today. Are quantum probabilities an intrinsic feature of reality or an artifact of the quantum formalism? How does the world transition from the haze of possibilities allowed by the quantum description to the single definite reality of common experience? How do we extend quantum mechanics from description of systems within the universe to the universe as a whole? Is quantum mechanics the rock-bottom theory of reality, or will it prove a mere stepping stone to a more fundamental description still awaiting discovery? As we peer into the future, insight into these questions will be essential for navigating the quantum universe. Good afternoon. Thank you. All right, so our subject today is quantum mechanics, and arguably quantum mechanics is really the most profound disruption to our understanding of the physical universe that our species has ever encountered. And part of the reason for that is the description of the world, as we just saw in the piece and as we will explore here today, The description of the world is so different from our everyday experience. And in a sense, perhaps we should not be surprised by that, because after all, our minds evolved in order that we could survive. And survival and the intuition that allows us to survive, it does not need to know about the behavior of electrons and atoms and subatomic particles. This juncture between how we experience the world and how we understand the world through observation and experiment will really be what will guide our discussion here today. We've got a number of wonderful scientists to help us think through some of the key issues. We have Elise Crull, we have Sean Carroll, we have Carla Ravelli, and let us now turn to the first of those conversations with Elise Crull, who is an associate professor of philosophy at the City University Graduate Center and City College. Her research explores the philosophical dimensions of quantum mechanics, causal models, as well as relativistic and temporal entanglement. Thank you. So just to jump right in, Elise, I think all of us are familiar that, prior to, say, 1900, we had a pretty good understanding of physics, right? Through the ideas of Newton and Maxwell and so forth. And then it began to crumble, right? And as it began to crumble, a new paradigm came on the scene. I want to explore that paradigm, but you've written on the history of the subject, and I think many people perhaps don't fully appreciate how much of a psychological and emotional upheaval this time was for the discoverers of these ideas. Can you just give us a sense of what it was like?
Sure. Well, I can try. I've felt that sort of cognitive dissonance myself, so there's some first-person experience. But yeah, there was a famous speech given by Sir Arthur Eddington, not Eddington.
Lord Kelvin.
Thank you, Lord Kelvin, one of the guys in the history of physics.
They're all the same. Yes.
He said there were just a few clouds on the horizon and we've nearly solved it all. We have Boltzmannian statistical mechanics, we have Newtonian mechanics, we've got Maxwell's electromagnetism. There's just a few issues, and one of those issues was black body radiation, and that's just basically if you've seen an oven, there was a known correlation between the color or the heat inside of it and how it radiated back out. And there was no good model for it, and so Planck sort of looked at the empirical data and said, I don't quite know what the underlying story is here yet, but I can cobble together a mathematical structure. I can posit this idea that light acts as though quantized.
And quantized little pieces.
Like in bits, yeah, not just a wave as it had been thought. And this captured, the empirical data correctly, but Planck hated it because he said, I don't know what my own math really means. And it took until Einstein in 1905 and then in 1909 to sort of provide that background story, and Einstein wasn't happy with the background story either because it required two terms in the equation to solve black body radiation. One of the terms was wave-like, continuous. The other term had H, Planck's constant.
Yeah.
It was quantized, it was about bits. And there they were sitting together in this equation. And that's how we know it to be today.
Now, is there something odd about the idea of not being happy with the mathematics? After all, if the mathematics describes the data, and that's ultimately what physics is meant to do, why would someone be unhappy with it?
Oh, because I think we're interested in the deeper explanations, right? Or at least that's what physicists tend to be drawn to. And mathematical mapping, like capturing of the phenomena, is a part of it, surely. But how that mathematics is supposed to lend insight into the real behavior of things. If that's missing, then you've solved a puzzle, but you haven't explained the nature of the universe, and that's sort of the driving motivation, I think, for many of these.
And we'll get into the details of quantum probability waves and issues like the measurement problem in just a moment. But given that well-articulated view of what physicists are trying to do. Where would you say we are right now today with quantum mechanics?
That's a great and large question. So, I mean, I'm primarily a philosopher, so I get sort of this perspective, so don't take it personally if I say something you don't like. But I think it's actually a really exciting time, because we're seeing exactly the limitations of models we've been working with for nearly a century now. I mean, the 100th anniversary of quantum mechanics is in 2025. And there's still puzzles, enduring puzzles, about how the mathematics really maps onto the world and how to explain a lot of the data we have. And this gets even more apparent when we get to the Planck scale, the very small, where our very well-confirmed theory of general relativity no longer sits well with our very well-confirmed theory of quantum fields and so on. And the
Planck scale, just to give people a sense of how small that is, 10 to the minus 33 centimeters is a number that we often kick around, so it's fantastically small.
Yeah, extraordinarily small. But I don't know, it keeps me awake at night to think that these two theories don't play well at that level. But it's an exciting time as a philosopher with physics training, because there's more engagement between philosophers and physicists, because we're talking about theories of quantum gravity and theories of quantum field theories and so on, that not every piece of them is empirically testable, or at least we haven't figured out how, or maybe in principle testable. So some of this is questions of how brilliant our engineering, how clever we can get about shielding our systems from external fields and so on. But part of it is just asking, can we have a broader notion of what evidence we might look for? Can we think about, for instance, whether there are systems we understand very well in a different realm of physics, like hydrodynamics or something, that might yield insights into how quantum gravitational systems might work? But how do you analyze the science of an analogy? Right? How do you know when the explanation from this one field that's well known, whether it's really saying something about this other unknown bit of the world?
Or whether it's just biasing the way you're describing the narrative that you're telling about the world, and it can go both ways.
Sure.
So getting in a little bit to the details in the background, in the Newtonian picture, if I tell you the initial conditions, you know, the speed and the location from which a ball, say, is thrown, the velocity to be more precise, Newton tells us where it will land. Quantum mechanics comes along and says that's not the case, right? So in quantum mechanics, there are many locations where, say, an electron could land given the same initial conditions, and that leads to this idea of a probabilistic description of the world, where you don't say where it's going to land, you just give the probabilities of where it might be. So one way that scientists were taken to this picture of matter is, of course, with the famous double-slit experiment, where you're firing particles at a barrier with two slits. You'd think that the particles would land on the detector screen in two lines that are aligned with the two openings. But when you actually do the experiment, of course, as we now know for over 100 years, you don't find just two lines on the detector screen. In fact, you find many lines, many bands in a very particular pattern, which scientists were able to explain by thinking of particles as waves, and as the waves hit the two openings and they carry on, they crisscross and they interfere with each other, and through that interference, we get a pattern just as in the data. If we interpret, of course, the waves as waves of probability, where the wave is big, many of the particles will land, where the wave is small, very few will land. So this now takes us to this new paradigm that particles, matter, should be described as undulating waves of probability. Did it take people a long time to accept that change? Because I would consider that, I mean, we'll talk about other things, but that's like the dominant new idea that comes into the story.
Well, Brian, I'd argue that there are many people who still haven't accepted what quantum mechanics is saying is that we have an irrevocably probabilistic universe. And so there are many interpretations that are offered of this mechanics that are supposed to fill this gap, explain why it is that the formalism that's sort of shared amongst the interpretations, this sort of core bit of explanatory work, maybe what you read in your quantum mechanics textbooks, which you all have at home and will study later this evening, right? But the story there is that, yeah, we have the Born rule, which is this rule that tells us what sort of probability to expect which outcomes.
Yeah.
But no thoroughgoing causal story of how we get from point A to exactly point B, a well-defined, localized spot or measurement.
And that story that you're referring to would start with this new probabilistic idea. Electron 30% here, 22% there, 19% there, and so forth. Go from that, which we don't experience, somehow transitioning to when we measure the electron, we find it at one location. So a kind of schematic representation where the height of this wave is meant to indicate, the likelihood of the particle being at one location or another. That's the story that we don't experience. But then we go and measure that electron. Let's just do it together. 3, 2, 1. Measure that electron.
Ooh.
Wow, that felt very powerful to do that. But now the probability has spiked because now we've measured the electron. We know it's at that particular location. How in the world do we go from this weird probabilistic description upon measurement to a definite outcome?
Well,
that is a deeply unfair
He's
question.
He's asking me to resolve the interpretation problem for you.
Or even just tell us why it's so hard.
Yeah, well, so first of all, I just want to clarify something a little bit. I mean, it's true that at the macroscopic level of tables and chairs and other people, we do see what look to be definite outcomes. But if you're doing measurements on smaller systems, you can measure what are called interference terms, and we call those sort of the residue of the wave-like features of those systems. And so they're there, and we're getting better at testing, like keeping interference terms coherent to higher and higher levels. So the idea is if we had really brilliant engineers and really good shielding, we could send an elephant through a double-slit experiment and see the elephant sort of give us a interference pattern on a screen. But the idea is that the appearance of the classical world and definite outcomes, we have a pretty good physics story for how that works, and it involves what's called quantum decoherence. And it's basically that the entanglement of two systems, there's a way that they can communicate with one another once they're entangled. And if you're in an environment with many, many degrees of freedom, ways of being, that's sort of a poetical way to put it, I suppose, many parameters, then those can sort of damp the interference terms down if they become entangled with you. And so those waves, the wave peaks that might give rise to a smeared cat that's dead and alive or something, get damped down so that we'd have to do measurements over many lifetimes of the universe before we might see something non-classical looking.
So this is possibly an explanation for why it is that the weirdness of quantum mechanics doesn't come up to the macro world.
Right.
Because it's a messy macro world with all sorts of interactions. You have the cat over there, photons are bouncing off of it, you're maybe petting, all those interactions affect the quantum description of the cat. And the idea of this quantum decoherence is those interactions tend to suppress the very parts of quantum probability that are at odds with our experience, which is why our experience is as it is. I mean, is that a widely accepted perspective now, would you say?
Well, it should be because it's right. But in fact, I think to be less flippant about it, those who are working seriously on realist interpretations of quantum mechanics will all use decoherence to explain a huge chunk of their story, and then they'll bring in either a spontaneous collapse of the wave function to get from mostly damped
which is kind of what we saw in that little example.
That's what that, or you could say that many universes come out of it, and you'll hear more about these different things later on. I want to say that those interference terms are still there, and there are experiments done where we can recover these terms. And in fact, our whole hope of building quantum computers that are, powerful enough is that these quantum qubits are in entangled states with one another, and that's how we get more than 0 and 1 as our values, and we have a more powerful, more expressive machine. But entanglement gets destroyed by decoherence. So the whole game in building quantum computers is to shield it from this very thing that hides the quantumness, as it were.
Now, you mentioned the word entanglement a couple times, and it'd be great to spend a little bit of time talking about that. So you've actually written on the history of this idea. I mean, just give us a thumbnail sketch going back, say, to 1935. Maybe that's a good year to focus upon.
We can scoot a bit back further.
Please do, yeah.
So something that you learn when you look at the history of physics is not only that there aren't geniuses sitting alone in a room somewhere, even Heisenberg on Helgoland, I know, I'm sorry to break it to you. They're in communication with one another, they're bouncing ideas off. Schrödinger was having many conversations in 26, 27 about the nature of his wave function. He published a series of papers in 1926 exploring what the wave function could do for quantum systems. But he was still troubled, and you see in his notebooks, which are written in a cryptic German shorthand, so a lot of fun to decode. If anybody feels like doing a puzzle later on, there are still some notebooks to be translated. But he starts thinking like there's this strange feature of interacting systems in quantum mechanics that doesn't appear elsewhere. And we see him talking about this, and he sends letters back and forth with Einstein in 1935, exploring this concept more. And at the end of 1935, he publishes a paper in which he baptizes this strange interconnectedness of systems, such that even when they've ceased to interact, they still cannot be described without making reference to that other system. So our notions of Newtonian individuality, where I can give you the list of properties that belong to this thing, and that state belongs to this object. If this is entangled with other stuff, I can't write down a state of its properties all by itself. It's instead, I have to describe it by making reference to all these other objects. And he calls it entanglement. So it gets named for the first time by Schrödinger at the end of 1935, but the idea is in the air, and it's being talked about by Schrödinger and Einstein and a philosopher of physics, Greta Hermann, and others. So it's floating, but nobody really wants to accept it.
And I think we even have a quote
Yeah.
of Schrödinger, but you probably know it by heart. But I would not call that, referring to entanglement, one, but rather the characteristic trait of quantum mechanics. That's this notion that you can have two things that are not next to each other, and yet you can't describe either independently of the other. Very, very strange idea. We're used to a world that's sort of local, right? What happens here, happens here. And you don't need to think about stuff over there to describe what's happening over here. And then in 1935, Einstein writes a curious paper on this, which you've written about.
Yeah. Well, Einstein had less to do with the writing than he would have liked, but he co-authored a paper with Podolsky and Rosen, and Podolsky wrote it. Yes. Can quantum mechanical descriptions of physical reality be considered complete? And people have spent a lot of ink trying to get clear on what the logical problem or paradox is there. But in a letter to Schrödinger, Einstein says very clearly, like, aside from what's printed in the paper, my issue is that you Schrödinger, your wave function doesn't...
Which is that spread out blue probability wave,
doesn't tell me like which state will come out in the end for a given system that I measure. And Einstein's thinking that all these physical systems in the world, even if they're quantized or whatever, have little flags on their heads with a list of properties that follow them around. But with Schrödinger's new mechanics, it looks like there's a way that the flag has other properties of other systems, and I can't predict.
So my flag sort of depends on your flag if we're entangled in this way.
And that I can't give a complete description at the beginning of my experiment which wave function will end up describing one system at the beginning. There are multiple mathematical descriptions of the final project, and he wants a one-to-one correlation.
Can we give a concrete example? I think many people are familiar, at least at one level or another. But before we show any visual, we'll use the so-called spin-a-half particle. It's a technical term, but basically, I think as many people know, every particle in the world spins around at a fixed, non-changing rate, but that rate can be either spinning clockwise or counterclockwise. We call one spinning up, the other spinning down. This is a known fact about particles, but in the quantum world, much as the cat can be sort of part dead and part alive, the electron can be sort of partly here and partly there, the spin-a-half particle can be in a blend of up and down at the same time. Can we just see an example of a single spinning? There we go. Right? So again, much as measuring the position, you can measure the spin. So if we can do that together, 3, 2, 1, measure. There it is, right? And it happened to come out up in that case, but if you let it, another example, if we can just do it, have that guy going
Let me
on.
do it this time.
You got it. I don't know if you got the power, but try it.
3, 2, 1. Ah.
You do. Look at that. Fantastic. Now, that's weird enough, right? Because this is the example that you began with by saying, you know, you've got this probabilistic haze of possibilities, and upon measurement, somehow one is selected. That's weird, but let's accept it.
Okay.
Because now we want to talk about what you were focusing on a moment ago, which is entanglement. And to do that, let's bring up 2 of these particles that have been set up, and I'll let you do the honors. So why don't you measure just the particle on the right? Don't touch the particle on the left.
Okay, 3, 2, 1. Oh,
Very well done.
There was
Very
sound
well done.
that time. Okay.
So the point is, by measuring the particle on the right and getting it to have a definite quality, you force the particle on the left to have a definite quality. That's the correlation, which is weird, right? Einstein called that spooky, right?
Yeah. Well, spooky because we have to imagine these guys are so far apart.
Oh, they're on the opposite ends of the universe.
Yeah, they couldn't have sent a signal to one another, say, hey, particle 1, I'm going to be spin up, so how about you be spin down?
Yeah.
So there's no signaling theorems that show that quantum mechanics, these separate measurements correlate to a higher degree than we can explain classically. And we call that non-locality. And that is in many ways a signature of entanglement of these systems. And they're not talking to each other.
So how does it happen? I'm so glad I'm asking the questions.
You'll have to attend one of my courses where we'll solve for you. There's much we don't know about entanglement, and different people will define entanglement differently. And in fact, many of the experiments that we've done looking for these non-classical correlations are Bell-type experiments to show that Bell's inequalities are violated by
And that's
quantum
something
mechanics.
we'll actually talk about a little bit in the next conversation, but yeah.
But they look at 2 systems separated in space. But of course, we live in 4D or more, as you like. And so what's really happening, these measurements are not just across space, but they're also at different times.
Yeah.
Technically, right?
Sure.
And so entanglement is a property of space and time. And so there are these really clever experiments being done to think about the temporal aspects of entanglement. Because you can understand maybe there's some spooky whatever connection between things at a spatial difference. But how could it be that through time they're communicating? So in fact, there's, I think you might have a slide.
Yes, I think,
for
can we bring up Elise's, so tell us what we're looking at here.
So this is roughly based on what's called an entanglement swapping experiment, and it was done at Hebrew University in 2012, 2013. But basically you're looking at, you see particles 1 and 2 are entangled photons, just like we just did our little experiment with.
Yep.
So if you follow their trajectories, entanglement, or let's see, so 1 and 2 get entangled, but then we measure 1, we kill it off, right? But we send 2
and when
bouncing.
you say kill it off, you mean you've now changed its properties through this measurement, absorbed the particle or whatever. Yeah. Good.
Yeah. So I mean, Schrodinger's equation is deterministic, so it's classical in a sense that it gives us values for all. But as soon as we do a measurement, it kicks that evolution out of unitarity. But okay, so we do a measurement, so we can't say anything further about.
Particle
that guy.
1, yep.
2 we send bouncing around on all these mirrors here for a bit, so just forget about 2, Meanwhile, at T3 here, time 3, we create 2 more entangled particles, 3 and 4. And we do a special measurement at 2 and 3. It's called a Bell-type measurement, and it just does something called flips the entanglement. It takes the entanglement from 1 and 2 and flips it onto 2 and 3. So the entanglement of 1 and 2 and the entanglement of 3 and 4 gets swapped onto 2 and 3. But then we take 4, and we finally later on do a measurement of 4. Now what's interesting is, look at particle 2 over there. He lived between T1 and T2. Sorry, particle 1 lived between T1 and T2, and then died. And over here we have particle 4, which lived between T3 and T5. So in the lab frame of reference, particle 1 and particle 4 never coexist. And yet they measured polarization angles that are
like spin
that are non-classically described. So they were entangled. Those particles that never lived at the same time,
Wow.
nevertheless knew what values they should manifest such that they would violate classical statistical correlations. And that's pretty cool.
That's kind of crazy by any classical reckoning. And so, what is this? I mean, it's still very much a story in the making, but just in our last couple minutes here, what do you make that this is telling us? I mean, is this giving us deep insight into the nature of space-time, some kind of entangled quality, which other areas of physics have certainly been suggesting?
Absolutely. I think that entanglement really forces us. So the line after Schrodinger's, the finishing of that sentence, is not that it's just one, but the, and the is supposed to be italicized in the original, the description that forces our entire departure from classical lines of thought.
Yes.
Our minds are still, here's a physical object, it's relatively isolated, I can list its properties, and those properties belong to that system.
Yeah.
We just can't think like that anymore, because entanglement showing us that how we define systems, there can be properties attached to those systems that don't obey the usual stories. But then you can think that the story I told before about, when we did our clapping and we got the entangled, and then I just showed you entanglement in time, but we're still talking about polarization or spin, a property being entangled over space-time.
Yes.
But there's this further question that if space-time is quantized, as many think it is, then space-time itself could be in entanglement relationships. And that is pretty cool also. I think maybe there's another image that can show up.
Yeah, let's see Elise's final image, if you would. Yeah.
So, I mean, we don't think of space-time as a physical object like, a Rubik's Cube mini block or something. It's clearly not that kind of substance.
Yeah.
But it ain't nothing, okay? Even Newton understood that space-time was some kind of substance, not like a material body, not just a force.
The spinning bucket of water is how he got to that conclusion, but yes.
Right, and so there's a way, if space-time can be curved, so it can have properties, right? Then surely it can have, if it's quantized, the quantum property, namely entanglement. So it could be that, I've drawn these beautiful little arrows here to illustrate, this little brick of space-time, and I've compressed one of the dimensions, you choose which, and the other up over there could be entangled such that, well, the nature of space and time are not a sign of, bodies sitting in those places aren't sitting in a region of space. It's mind-boggling, and I'm just beginning to work on it. So
it's a deep interconnection woven into the fabric of space-time itself
Absolutely.
in principle.
Absolutely.
Fantastic.
Yeah.
Please join me in thanking Elise Crull.
Thank you. Thanks
Thank
for
you.
being.
That was wonderful.
All right, that was an enlightening tour of the basics of quantum reality, including the probabilistic nature of quantum physics, the remaining mystery of how a seemingly definite, classical-like world can emerge from one that is inherently quantum mechanical, and finally, the wonderful weirdness that so concerned Einstein but has now become commonplace in our applications of quantum physics, namely the non-local qualities that arise from quantum entanglement. And these are qualities that may well be at the heart of how space-time itself is stitched together. All right, with that quick summary, I now encourage you to continue your journey with our second conversation in this quantum reality series with our guest, physicist John Carroll, in which, among many other things, we will explore the many worlds approach to quantum mechanics.